This video is about how to draw a line of best fit effectively. Before we can talk about lines of best fit, we need to introduce the idea of error bars. Error bars give you a visual representation of the uncertainty on your graph. As you know, all your data that you've measured should have a reading and an uncertainty associated with it. Here we have some data for distance and an uncertainty of 0.01 meters for distance, and we have some readings for time. We have 3 values of time for each distance, an average, and then an average uncertainty here. So both of these data points give you 2 readings and 2 uncertainties that we'll have to plot in a graph. Error bars produce an error box around the point. If you can see here we have 2 plotted points. We have distance time 0.4, 0.19 plotted here, and you can see around it there is like a little blue box. Now that little blue box is drawn with the help of the error bars, and they show you the range of possible values that could exist. Again, we have another point here, 0.5 and 1.48. And around it you can see that there's error bars. So that's what we're aiming for. Either error bars or, if possible, an error box around each point. Now you use your uncertainties to draw the error bars. Error bars are simply a small line on either side of the point with a vertical finish if it's horizontal, or if it's a horizontal error bars, if it's a vertical error bar, a little horizontal finish at the top. And that's how you draw them. Just a line to represent the uncertainty, and then perpendicular to it, a little line to end it. When you're drawing them, please don't make these lines bigger than these lines. It's distracting and it shows a kind of clumsiness that you don't want to be associated with. So the uncertainty should be clear, and the little stoppage here should be a small little line. Now, how do we draw these? Well, using the scale of your graph, you are going to represent the uncertainty. So in this example, here we have a plotted point and an uncertainty, which it says here, look on the y-axis, the uncertainty is approximately 0.4. So what you have to do is plot 0.4, a distance of 0.4 using the error bars. How do we know that distance is 0.4? Because we're using this scale. So you find 0.4 on the scale, and it's plus 0.4 in this direction and 0.4 in the other direction. And then you draw your little stoppage line underneath it. You could see also in the horizontal, the error bars are equivalent to 0.1. As you can see on this scale, 0.1 is 2 small divisions. So we have 0.1 in this direction and 0.1 in this direction, plus and minus 0.1. Now, why is there sometimes a box and sometimes there isn't? Well, if your uncertainty is too small to draw, so let's say your uncertainty here was 0.001. Using this scale, you can barely see 0.01. It's negligible. So if your error bar is too small compared to the scale that you're using, then you just assume that it's negligible, and you end up with this situation here, right? But if they're actually valid for 2 different directions, then you end up with this kind of square arrangement. So if you go back to our original situation here, you can see that we have the 2 points and their relevant uncertainties, which are 0.01 on the distance scale. So distance here, our point has a uncertainty of 0.01, so we do 0.1 this way, 0.1 this way, and that gives us our error bars in this direction. And then for this value, we have 0.02. Now, here we can see it's 0.02, and we go down here and we measure 0.02 in the vertical direction because time is on the vertical scale. Remember that, just to add this little extra point, We also have an uncertainty for the instrument, but we're ignoring this because the uncertainty due to the averages is so much greater. Okay, so we can ignore that one. Now, of course, we're doing this so we can draw a line of best fit. So let's go back to the idea of a line of best fit. Lines of best fit must be as close to a true trend as possible. So when you have scattered points like these representing random errors, your line must be as close to the plotted points as possible. You have to try and balance these ideas because you don't want to, you might have to disregard certain points more than others, right? But what you have to do is kind of get your line through as many and as close to as many as possible. It doesn't even have to go through any of the points, but it does have to go close to all of them. Now, when we have a situation like this one, then it's a bit of a rough situation, right? Because what you're doing is approximating. If you move this line a little bit further this way, then you're closer to these, but less close to these. Anyway, it's just not very accurate. It's not a very accurate way of doing things. And that's why error bars are great. Because error bars, they give you the range through which you can possibly go. Error bars represent uncertainty. So basically, you don't have to go through the points anymore. You can go anywhere within the error bars. And that gives you a hard and fast rule for drawing your lines of best fit. When you have uncertainty bars, you must make sure that the line of best fit goes through as many uncertainty bars as possible, paying more attention to the smaller uncertainty bars than the bigger uncertainty bars. Ideally, your line of best fit should go through all your uncertainty bars. And if not, then what you've got there is an error, a point that you have to discount completely. Uncertainty points or uncertainty bars that are smaller means that there's less range of uncertainty, and so those are the ones which consider to be more accurate. And you should go through those before you go through the ones with the longer bars. If you have error bars that are enormous, then what you're probably going to have to do is think about how to do your experiment again. But we'll come to that a little bit later on. Last point with drawing lines of best fit. Use a ruler if you're doing them by hand, and make sure that you have an even spread of data points on either side of the line. This is something we'll practice in a moment. Lines of best fit when it's obviously not a line. Lines of best fit do not have to be straight lines. As we mentioned before, most relationships are non-linear. So make sure that if you see a curve, you draw a smooth curve to represent that relationship, not a straight line through the middle. Don't force a straight line through it. So line of best fits can be straight lines, or they can also be curves. Here's a nice example where we can see that there is an inverse relationship here, 1 over something, and the curve of best fit is a smoothly drawn curve which goes through all the error bars. Now this is what you're aiming at when you're drawing curves of best fit.